AP Classroom assignment on density. A couple words. While this is purportedly about density, a lot of it is really about Archimedes' principle, which is coming up later in section 1.5. But we'll talk about that more in class. Here's question 1. A student predicts that the density of salt water is higher than the density of drinking water. So here, it's important to notice that the student is just comparing with this word higher, the densities. The student has a beaker filled with salt water, a beaker filled with drinking water, and a cube that is hung from a spring scale. I attempted to draw that here. The cube will sink in both liquids. What measurements are needed to verify the student's prediction? So I drew a force diagram here, and the salt water is denser. And if the salt water is denser, that means that this buoyant force is going to be greater in the salt water, making the tension force, and this tension force is what the scale reads, that's going to be less as compared to the drinking water. The buoyant force is less. Oh, that was fun. The buoyant force is less, which means that the tension force, or what the scale reads, is more. So again, this tension force is what this, oh, come on now. This tension force is what the scale reads. So by comparing what the scale reads, I can figure out which one has more buoyant force, and the one with more buoyant force is going to have more density. So, I wrote that here. More dense, more buoyant force. By looking at the tension force or spring scale reading, we can compare those and we can verify which is more dense. So answer C. Question number 2, we have a table here. We have 10 objects. We have their height above the water, their length, their width, and their height. And it says, in an experiment, rectangular solid objects of varying sizes made of the same material are floated in water. The data table gives the dimensions of each object and how much of that object is floating above the water. This is another idea that comes up when we study Archimedes' principle, and I'll be giving some notes on that in a different video, but I'll be touching on it here because we need to. Which 2 of the following variables together can be used to calculate the density of the object? Okay, so first of all, let's think about this for a minute. We've got a vessel of water. Just a reminder that one thing that's handy about water is that the density of water is 1 gram per milliliter, or 1,000 kilograms per cubic meter. So water is really easy to work with because we've got this magic number 1. Remember that the metric system also is based on water. We know that 1 gram of water is equal to 1 cubic centimeter of water is equal to 1 milliliter of water. Anyway, in this case, we've got a cube, and it's floating with part of the cube out of the water and part of the cube submerged in the water. So I've labeled here H under, that's the height of the cube that's underwater, and then we've got a length and a width measurement, and then this total H is the total height of the cube. Another reminder that for floating objects, the buoyant force and the force of gravity are equal and opposite. So I've written that here. Okay, so here's what we know. For an object that's floating, the buoyant force is equal to the density of the fluid times the volume of the fluid times G. And this density times volume, that's the mass of the fluid times G. This side of the equation is also the weight of the displaced fluid. On the right side, we've got the Fg, which is the mass of the cube times G. I can cancel out the G's, and then I can make a substitution. This is supposed to say VU for the volume underwater, and the volume underwater in this question, the volume underwater is the length times the width times the height underwater. So I've put that here, and then the volume of the cube itself is length times width times height, so I've made that substitution on the right side. And then I canceled length and width, and you'll see what we're left with is the densities and just the height underwater and the height of the cube. So those are the two things we need. We need the height above the water or under the water and the height of the cube. So this brings me to another point I need to make about Archimedes' principle. For floating objects, the buoyant force equals the force of gravity. And again, I'm rewriting what I said before. That's the density of the fluid times the volume underwater times g equals the density of the object times the volume of the object times g. If I cancel out g and rearrange this formula, I end up with this statement, that the volume of the object that's underwater over the volume of the total object is equal to the density of the object over the density of the fluid. And the left side of this equation is the percent of this object that is underwater. So that's this. What percent of the object is underwater? This is a super handy formula, and I am going to refer back to it repeatedly as I go through this lesson or these problems. So again, percent underwater is equal to the density of the object over the density of the fluid. Also keep in mind, again, that the density of water is 1. So really, if something is 80% underwater and it's floating in water, then the density of it is 0.8, because 0.8 over 1 is equal to 80%. So that's pretty handy. Okay, question 3. Students have a sample of an unusual fluid. The density, rho f, of the fluid varies with the temperature to a much larger degree than most fluids. To investigate the relationship between the fluid's density and its temperature, a wooden cube is allowed to float in the fluid. The temperature of the fluid is varied and this unsubmerged volume of the cube is measured. Okay, so going back to this picture, again, we were talking about the part underwater. Now we're talking about the unsubmerged part, but it's still the same idea. It's still this idea of the percent underwater or the percent above water. The upward force exerted on an object by the fluid is equal to the product of the density of the fluid, the volume of the object that's submerged, and the acceleration due to gravity. Which of the following must be known for the density to determine the density of the fluid at various temperatures? So again, what I did was I used Archimedes' principle here, which says that the weight of the object equals the buoyant force. The weight of the object is mg. The buoyant force is rho times volume times g. And in this case, the volume that we want is the volume submerged or underwater. Notice this VU is the unsubmerged volume. So the underwater volume is the total volume minus the VU, the unsubmerged volume. So that is why that one is the answer. Number 4, an engineer is designing a device to measure how the density of seawater changes with depth. The device consists of a hollow spherical metal container. Okay, so that's what I have attempted to draw here. Here's my sphere, and it's hollow, so there's a hole that I can put masses in. It's of known mass and volume and can hold weights of known mass. The weights can be added or removed without changing the volume of the device. So there's an opening here for masses, and I can take masses and put them in here to change the mass of the device. The seawater exerts an upward buoyant force on the device given by FB, that's your buoyant force, equals rho times volume times g, okay? We've seen that before. This, again, means rho means the density of the seawater. V means the volume of the device. And I want you to notice I've drawn this with the device just underneath the surface of the water. So the device is completely submerged. And G is, of course, 9.81. Let's see. Which of the following correctly explains how the device could be used to measure the density of seawater at a particular depth? Okay, so if we had this thing sort of suspended in the water, So it's completely underwater, but it's suspended in such a way that Fg equals Fb. It does have kind of a buoyant force. It's not touching the ground or not touching the bottom of the container. It's above the bottom of the container. Then what we would do is we would add or remove weights until the device is in equilibrium, and then use the known mass and volume to determine the density of the seawater. And again, we would be able to do that because we know that the buoyant force equals rho Vg. That's rho is what we're looking for. And the buoyant force also equals the mass times g. So basically, if I had the volume and if I had the mass and g would cancel out, I would be able to find that density. Number 5, a student wants to determine the change in density of a liquid. Number 5, a student wants to determine the change in the density of a liquid as a function of its temperature. The student has various measuring devices and some blocks that will float in the liquid. The upward force exerted on the objects by the liquid is equal to the product of the density of the liquid, the volume of the block that's underwater, and the acceleration of gravity. This whole chunk is really just saying this rho Vg again. Just a reminder that density times volume is mass. So the upward force, it's basically just saying that the buoyant force is equal to the weight of the water displaced. Okay, which of the following is an appropriate experimental method? So just a reminder that what we're looking for is density, and density is equal to mass over volume. So it's saying if we had a known mass of the liquid, and if we recorded the depth and we knew the cross-sectional area, we could figure out the volume. So that would be one way to determine density. Part C is correct because we're looking at the height of the submerged object and how that changes. That really gets at this percent underwater concept. If we could figure out the percent underwater, then we could figure out, the density of the fluid. We'd also need to figure out, we could calculate the density of the object if we knew its mass and volume, and then we could determine the density of the fluid. Number 6, a student has 4 pieces of a substance in different shapes and sizes. The student wants to determine the density of the substance. Which of the following procedures would yield the most accurate data? Again, density is mass over volume. So part A doesn't work because it doesn't get at the volume of the object. Add enough water to cover pieces and record the volume of the added water. We need the volume of the object. B, place the masses on a balance, record the mass, submerge the pieces in a graduated cylinder, and get the volume. So again, mass and volume is what we need. C and D do not give us mass and volume, so C and D are not correct. Number 7, a student has 3 objects of different shapes as shown and wants to compare their densities using liquids of known density. Which of the following experimental methods will allow the comparison to be made? This is another one with percent underwater, which I've written again here. Let each object float in the same liquid. Compare the fractions of the object's volumes that are below the liquid's surface. None of the others get at that. Number 8, a student has 3 objects of the same material and shape but of different sizes as shown and wants to determine the density of the material. The student hangs each object on a scale and submerges each completely in a liquid so that 3 data points may be obtained. Which of the following steps is required to be sure that all 3 data points are valid? So if we are hanging an object on a scale and submerging it in a liquid, which I've drawn, this is in the process of being lowered into the liquid, you can't let the object touch the bottom of the container, because if it were to touch the bottom of the container, then you'd have a normal force from the bottom of the container, and that would mess up your measurements. We would just want the scale tension to be read. Finally, number 9, the following data are obtained from different sources and investigations. Which of the following represents the order of substance densities ranked from greatest to least? So again, density is mass over volume. They give us the weight. If you take the weight and divide by G by 9.81, you will get the mass. So that's the 20 over 9.81 is the mass of the gold, and then I would divide by the volume and get the density. So I've listed the densities, and the proper answer is gold, silver, copper, iron. Thanks for listening, everybody. See you.